So, is it already time? Yes, it is time. So, guys, you are very much welcome at this lecture. So, this is a new tradition of the house. So, I don't know, Nima knows maybe better than I do. Which lecture is it? Third, fourth?
For you, it's the first, so it's just
okay.
Your lecture.
For me, this is the first lecture. So, it's called Beyond the Classroom, when professors of the school are trying to present some nice fancy stuff, and actually because this is almost a Christmas time, so I decided to go for some nice fancy mathematics. And today I will try to give you a little bit of a flavor of a long-stand open mathematical problem, maybe one of the really ancient ones. And the problem is formulated very easily in the following words. When not is not a not. You will have the complete idea what does it mean a little bit later. But let's right away, without any ado, start. So, do you know what not is? Everyone should know, right? So we are all kind of wearing the boots and doing some nice stuff with ropes and stuff like that. So basically, mathematicians, well, do not read mathematical definitions. So I will just speak about birds and butterflies in this talk, so you can really survive easily without any mathematical notions that probably pop up on the lecture slides. So basically, if you have, well, some rope and you identify two ends in this, so just like that, so you have really a circle, right? So this is one of the possible knots. You can, of course, sophisticate it. You can really turn it upside down and put one strain inside of another, and this will be really complicated stuff. And again, in the end of all this process, you identify two ends. This is again a knot. Maybe the same, maybe the other, so we will see later in the lecture how it goes. So why do we actually, first of all, what is your intuition? Why should we identify two ends in the end of this strange manipulation? Just guess. Why mathematicians would like to have two ends identified? Why not to just you know, to have a strain?
For science.
Very good answer, yes. Partially to impress each other, yes, for sure, for science, yeah. For sophisticated stuff. Anything else?
So if you don't know these ends, where are the ends, when you cannot identify where is it a knot or not a knot?
Because everything is just a strain. Okay, yeah, fair enough. You wanted to say something?
I was going to say something similar, that, you know, when you are still able to identify the two ends, that's when it's still not.
Good. All is nice, but not correct. That's clear. So actually, mathematicians like this because there are less objects to play with. So this system is much less sophisticated than a string actually. And why? Because there are imagine that in the world there is this object, right? Then in this space, in this very room, there are only two types of points. The point on a rope and the point out the rope. And there are no, and if it would be really kind of something like that, then you have to identify the third object, which is the endpoints of the strain, which are totally different from all other points. So you have a third object, and system with three objects, obviously it's much more difficult or much more easier, so it really depends. So then the system with only two type of objects. Okay, anyways, let's continue. So the cycle, anything really kind of very strangely blended with identified ends, all of these subjects in the space we call a knot. Okay? Good. And now we have a really nice exercise. So I brought here a couple of ropes, and we are trying to actually to master a couple of knots. So here I'm talking about the Saylor knots. And of course, you see loose ends. And this is already a contradiction to my previous statement. There are no loose ends, right? But what you can easily imagine, that the loose ends are either attached to masts, or they are joined with each other, or two people. So for instance, for the ropes that you have, imagine that one person is keeping one loose end, another person is keeping another loose end, and you are trying to master this. So a third person in between those two masters these really nice, beautiful Saylor knots, okay? So it's not that these are loose ends. This is either identified end or two people are holding them, okay? And of course, you've seen the first slide, you've seen the invitation. The question is when knot is not a knot, right? This means that I want to give you really an idea that knots are quite different. They are different really even in mastering. So for instance, let's have a look at the slip knot. So this very, very first one. Do you think you can really somehow unfold it such that it becomes one simple cycle? Yes or no? And how to do it? So tell me just the procedure. What would you do to make it unknotted? Right, so you just pull two ends, and then, well, apparently it becomes just one strain, right? Or if we identify two ends, it will become actually one simple cycle, or we call it unknot. Okay. But now I give you a little bit more sophisticated. So you do have your strains, your knots. How do you master this first one, the slip knot? Do you think it's easy? Do you think it's difficult? No. How?
I think it's difficult.
It's difficult. No way. Look.
That's a me issue, I think.
Okay. So this is maybe everyone in the childhood liked to make these knots which you just pull and this falls apart, right? This is one of those. This means that this is easy to master. Yes, you see, that's quite simple. So you take two ropes, then you make just a cycle, right? You put inside the cycle the same two ropes. You pull it out. This is what you have initially. But you see that this one, it has, so actually, doing this, we created this bow line on a bite. This is the one. But what is the difference between these two? So you probably do not recognize, but believe me, this is true. So, but how to make this one? So you see, here we have two strains. You just take one outside, and you still have the same knot, but a little bit easier. That's how you do. Okay? A little bit easier exercise would be this cat's paw. This is really simple to do, right? It's simple to master. So how do you do it? You take actually two hands, strain, and you start twisting them. And without actually any problem, you have the cat's paw. Okay? And again, everything is doable when these two guys, these two loose ends, are actually identified, or if anyone holds them really tight between two masts or in the hands. More interesting thing, and here comes the trick, and here comes the first mathematical question. If you do have these two identified loose ends, can you master overhand?
Can you mark still what?
The third one, so overhand. Intuition tells not, right? Can you ever do it? Think for a second and give me any idea. Do you believe me that, well, we cannot do it?
Can't.
We cannot. So the only way to do this strange one, which is in mathematics, it's called trefoil, it's when you actually really make a sophisticated move like that. You really put one strain inside of a cycle. Well, there is even more sophisticated machinery. I will tell you later how this machinery works, because for that we need two-person. It's two-person game. So one will be holding arms like this, forming actually a cycle, and then later I will try to tell you how, with help of this cycle, we create such a beautiful knot. But the point is that right now I want to, well, this is still unknotted knot, right? So, and the overhand is something which you cannot unknot. And I want to show you the entire lecture will be about those knotted and unknotted knots. So what we can undo and what we cannot undo. Really, the entire lecture. And I told you this is probably the most ancient mathematical question ever. And so far, there is no person in the world who can do it. It's as difficult as that. So we cannot make a claim. So no mathematician in the world can create an algorithm that from sophisticated knot, whatever you do with this strain then attaching to it, you do not know how to unfold it if it's unfoldable. No one in the world. Okay, so this is just to give you some interesting notions. Of course, this knot theory has really direct applications. So one which everyone knows, this is about how to make the surgical knots. And in surgeries, why is it actually interesting and actual right now? Because nowadays, in the surgeries, the knots are done not by people, but by robots. And there are different types of robots. There are two-handed robots, one-handed robots, robots with 2 fingers, 3 fingers, 4 fingers, 5 fingers, 6 fingers, etc. So, but still, 2 hands, 1 hand. What can be done with 1 hand? What can be done with 2 hands? What can be done with 2 fingers, etc.? These are really big questions. And then, well, engineering comes in clash with mathematics. So what actually, by means of engineering, you can do, for instance, with 1 hand, 2 fingers, what type of knots you can do, what type of knots you cannot, etc. These are really big questions. These are ancient knots in medicine. So this is what is taught in the medical faculty here across the river. And these are probably also easy ones. So this one you've seen already. This one, the simple one, that is precisely overhead that we tried to master, which is not unknot, which is really the first but simple sophistication of the knots. Okay. And just to impress you, this is the benchmark instance. So this is the knot that mathematicians and computer scientists and data scientists are playing with when we are dealing with some type of algorithms or for folding, unfolding, for doing different type of manipulations. You see, it's not that dense, so it's, well, you can see, you can really follow the strains, But this is already sophisticated and complex enough that, well, modern machineries do not allow us to analyze what's going on with this. So seemingly simple, this is already hard enough for the modern computers. It is really sophisticated stuff. Okay. Once again, because this is mathematical lecture, I have to tell you what a knot is. I told you already this is a cycle. So the formal definition again, just disregard, ignore it. So something simple which you can really introduce as a simple, I don't know, torus as a single strain with this in the simplest form. This is a knot. And what we are trying to identify, we are trying to identify all these complex things which I can do with a rope, which can be brought to that creature. Okay? That's unknotting. And again, let's so we already thought that first, second, and this fifth one are unknots. What about inside clinch? That's more difficult exercise. So first of all, do you see it, how it's composed? So do you see all the crossings, which strain on top of another, etc.? No? Ah, that's nasty. Okay. But look, we will have, I was going to give you this as an exercise. So this, on this figure, this is probably the most complex unknot. You can still unfold it. Actually, to see this, you can see the following. So these two strains that should be identified here, right? You can first just pull a little bit down, and then you can actually identify them as a strain that goes just with really light band in this point, right? And then forget about these two loose ends. And then what you should do, you should actually, you see this cycle, you should take this part which we already identified as just a part of the strain and pull it inside this cycle, and then it will be just one twisted thing. And then you completely unfold it. So this is truly a knot. Okay? We can try to master it, but well, this one will be actually quite tricky to do. The first three are easy. This one is super easy. This one is tough, just with hands. Okay. And of course, the question that I'm asking is, having all these knots, can we really identify which ones fall to the category of unknotable and which are outside of this category? Of course, if you have good eyes, and I hope you do have good eyes, you should be able to make this exercise quite easily. This is famous unknot, and it's already a hint for you. You can unfold it. But this is one of the first exercises, non-trivial exercises, how to deal with unknots. Try to. Or just give me an idea. As the title suggests, we should be able to. But how? Okay, I like the way you turn the hands. Yes. So tell me what are you trying to do?
I'm trying to fold the upper two loops through the middle and pull it from backwards towards the front.
Very good. Very
Yeah,
good. This is
pull them out and then I unfold one
precise.
one in
So
the middle.
this way, actually, these two strands become on the sides, right? And then what remains in the middle is precisely this braid. And then you start just flopping this, and then it falls apart, and outside there is a bigger cycle. Very good eyes. Brilliant. Okay, so this was unknotted Goritz knot. And again, if you have good eyes, you should have noticed already that there are some knots which appear not with 2 ends, loose ends, but with, for instance, 4. Do we have here anything with 6? I don't think so. No, but with 4, definitely there are, right? So this one, the reef knot, and sheet band with toggle have 4 ends. And then my logical question to you would be, what is this even? Is it, what do I identify? How do I identify the endpoints? Because previously it was easy. There were only 2. But for instance, for that one, if you identify these 2 endpoints and these 2 endpoints, what do you have in the end? So you identify these 2 and these 2. What do you have?
2 strings.
2
cycles.
2 cycles, right. 2 are knots. Are knots or knots? So can we really can we do anything like putting them apart and having really 2 separate rings?
Instead of pulling them from the 2 sides, where it just not in the middle, you just get them stuck together, no?
Well, so my question is very simple. So there are 2 rings like that, and there are 2 rings like this. Do we have this or that? This. Wrong. Look at this. I mean, you identify these 2 loose ends and these 2 loose ends. You actually squeeze this guy inside of this cycle, and this comes here, and that becomes really 2 falling apart things. Yeah?
That actually kind of depends on if the ends are fixed or not.
Well, we said they identify. Yes.
But if they are movable, then you can actually.
Well, identified means this is really kind of glued together. Right? Okay, but what if we identify these 2 ends and these 2 ends, the upper ones and the lower ones? Then what does it do with the figure? This I don't know myself. No, I don't. Is it one thing, or it's still two things attached somehow? It's one. And then the question is, if it's one thing, is it knot or unknot? Can you really unfold it in such a way that
what would you say?
Sorry?
What would you say?
I would say it's a knot. I would say it's a knot. Good. If we have this 4, 6, 8, whatever even number of loose ends which we identify in such a way that we are making a couple of rings attached or detached from each other, we call such a thing not anymore a knot, but a link, because it's linked, knots linked with each other, okay? So, and but later in the lecture, we don't tackle them at all, because our theory is, well, our question is whether knot is unknotable. And if it's a collection of rings attached, that's not even a question. Okay, so we cannot make one unknot out of this collection. Good. And now the first mathematical theorem, which was proven back in, well, almost 100 years ago. And that's it's really a fundamental theorem for the whole knot thing. So for the whoever think in the knot theory about any theorem should know about so-called Reidemeister moves. So there was a guy called Kurt Reidemeister who proved the following. So if you do have two knots and you want to establish some equivalence notion, so this knot we can turn into that knot, okay? He proved the theorem that if it's possible to turn one to another, then it's possible applying only three moves. And the moves are quite self-speaking, very simple ones. So the first one, we call it a twist. So you have a strain, and the strain has a twist. Twisting and untwisting is the first type of move. The second move is poke and unpoke. So you have one strain, you have another one, and one just, it just slides on another, okay? This is poke and unpoke. And there is the last one, it's a slide, when you just move the strain behind the other two. You see it? So this one is moved down. And you can shift up and down. So with these three, so if not by breaking a ring, cutting the ring with scissors is not allowed. If you have somewhat very sophisticated knot or a ring, and there is another one which you want to turn the first one into, then you can do it with these three type of moves. And this establishes right away kind of equivalence between different type of knots. So if one is turnable to another with these three possible type of moves, then these two knots are equivalent. This is the same knot actually. Yeah? And if not, then are different. So if you cannot do it, then these two knots are different. And this is nasty exercise. Just let's try to think. We were just unfolding this Goretz unknot into the simple ring, right? Into the unknot. And if you ask me how to do it with this Reidemeister moves here, I wouldn't be able to tell you. Because, well, you remember your first iteration, that you were really kind of flipping the upper part inside, describing this in the sequence of Reidemeister moves would be already a sophisticated kind of description. It will be really sophisticated thing to do, okay? And that's why this Reidemeister moves, it's an obvious thing actually to do. So what is exactly the sequence? How we turn one into another? How do we establish this sequence of moves? And later on slides, I will just show you yet another example where it's clear that to get from, for instance, unknot, which is a little bit scrambled, the simple knot, it's not sufficient to make kind of one by one some easing. So sometimes you have to make first your knot even more complex, and only then it becomes easier. And that's also a nice and tricky part. Good. And this is also a very recent result in mathematics. You can see it's 2015. And this is the journal which is regarded probably as #1 in mathematics, where there is a paper that if you have this very blended, very complex thing, but this thing is unknotable, so you can turn, so there is a way to turn it into the unknot, then there is a sequence of those simple moves, twist, poke, unpoke, and the slide, unslide, that brings this complex thing to the simple ring. But the number of such operations will be, well, if you have, if I draw actually a simple thing, this is somehow a knot or unknot. We count the complexity of the knot in the number of crossings of two strings. So here, for instance, the complexity would be 1, 2, 3, 4, 5, 6, 6 crosses in this diagram. So this is a diagram of a node, so it's drawing of a node on the plane. And here we are saying that there are 6 crossings. And the number of crossings appears to be kind of a measure of a complexity. And then if number of crossings is the measure of complexity, so here we have 6, but imagine that you have 10 crossings in the diagram, 10 crossings. Then the number of Reidemeister moves to unknot the complex thing, according to this guy, is about, so 236 times 10, it's roughly speaking 2000, so it's 2 to the power of 10. And then to another 11, so it's basically 2 to the power of 20. This is, no, it's 2 to the power of 100. 2 to the power of 100. So it's 2 to the power of 100 moves that the guy suggests to actually to write down.
At most.
At most, yes, correct. So this is this indicates that even if people know that this is a notable thing, describing the number or sequence of all these simple moves that bring this complex thing to the simple one, well, you see, it's really drastic. So it's not exponential, and this is a good thing. So because, well, if it would be kind of exponential, so here it's an opposite. So C sits in the basis of the exponent, and the constant shows up in the power. So, and if it would be other way around, it would be much more difficult. But nevertheless, you can imagine. So, how people could even write down. So you know the solution exists. You know that this would be the length of the solution represented. Well, be my guest to really write down all these Reidemeister moves. So this is how sophisticated it is. And 4 years after, the same author, this is published recently, really this year or last year, in another good journal, Advances of Mathematics. And here he is claiming the following. So this claim was, so let me repeat. If you can unfold, if you can unknot, then you need this many Reidemeister moves. And here he is saying, if you cannot unknot, if it's really a knot, then he doesn't even mention here what would be the complexity of this kind of checking the procedure, whether this is unknotable. But he proved that we can also certify this is unknot with a number of iterations, if this is unknot. So here the crucial is the condition, if, then. All right? And both these results together, so this is mathematics. Don't pay attention to mathematics. I will explain in words what does it mean. In words, it means that if among you there is a person who really develops an algorithm that brings a complex thing to a knot, will become a famous mathematician. Because there is a long, in mathematics, there are 10 very famous problems. For each of them, there is a $1 million prize associated. So right now, maybe only 7 remain. So some of them were proven, and the most recent one was, you probably know, this Russian mathematician Grigoriev Perelman. He proved, well, I will not dive into this. One of the unsolved problems, it's called P versus NP. What does it mean? It means that, well, if you have a problem, here we have a problem, and the certificate, what does it mean, certificate? You know solution exists. So this is kind of yes answer on the question whether it's unnotable. Yes, it is unnotable. And then certificate is the way you write down the solution. If you can write it a little bit compactly, so not that long, so this was not long writing, by the way, so to the power of 11, it was not long writing. So if we have such a certificate, so we know how to write compactly the solution to this problem, then, well, if you solve the question, you find an algorithm that solves this problem. So it's not if there exists, then, but you solve this problem. So you basically find out all this sequence of the Reidemeister moves. Then you will get actually immediately $1 million in cash. I don't know, from some Clay Institute. They claim they have it. This is not the same problem, but it's somehow little follow-up, so which tells the following. So if you can certify the yes cases, so basically here we have if this is yes case, so if this is unnotable, we know that this is a compact certificate. And another story, no cases, it's not unnotable. This is a small certificate that certifies it's not unnotable. Then there is a belief that these problems are much easier. So if both ways are present, so you can certify the yes cases and you can certify no cases. This is called, well, at least mathematicians do believe that this is lighter versions of the problems than the tough ones where you have no kind of, when you are only on one side, so to speak. So, and this long stand open problem, is there a fast algorithm to recognize the unknot? Well, if you solve this one, you shed a light on this certification of yes and no, and you become really famous mathematician, although you don't get a prize because you are not solving the main problem. Well, I see you already tired. Good. Anyways, we are also interested in the case of not only unknotting, but also in the case of establishing equivalence between any two knots. So the first question I asked whether knot is unknot, it's equivalence of a complex structure to a knot. And now we are saying, okay, there are two knots. either a way actually to establish any equivalence between these two. And this problem is known also for ages. And Turing said in 54 that actually so far we are not even getting close to this, to answer to this question. And of course, the interesting would be to identify some cases when it's easy to do. When it's easy to say, okay, well, this is definitely not a knot because of this simple property, okay? And that's what mathematicians were doing a lot in the past, I don't know, 50 years. And there are really nice and very intuitive things which I will introduce next. So, for instance, a very interesting thing, you remember we had overhead. This is overhead, overhand, and this is a knot. How to prove that basically these are two different things and one cannot be turned to another? That was one of the first questions that I asked. And there is a very interesting invariant. Invariant works as follows. Imagine that, so you do have these trains, right? And you do have, before every crossing, so for instance, this part is completely, you can completely see this part, right? So here, you stop seeing this train because it gets just below the other one, right? So here at this point, you stop seeing the blue one. And here, you stop seeing the green one. And here, you stop seeing the red one. But the point is, imagine that you are coloring with three colors your knot, and your coloring strategy is as follows. So you are coloring what you can see, the pieces that you can fully see, in a color. Okay? You are using three colors, and actually, the invariant is as follows. So if you can color a knot in such a way that, so you do have at every crossing, if you have two colors, then you have three colors. So if you need more than one color, basically you need all three of them. Okay? Is it clear or not? Good. If you can color it with three colors, then it's definitely not a simple ring.
It's definitely not a simple.
Not a simple ring.
Ah, okay.
So it's not an unknot. And why is this true? Well, actually, you can even prove that so this coloring, when you color this way, your Reidemeister moves survive this coloring. So basically, look at this. So if you have, for instance, the twist, can we make here use of all three colors? No, because this is one and the same visible string. And therefore, well, at most, we can have here only two colors. And this means that, well, basically, we are not satisfying the condition of being three-colorable. The same story, so if you make any kind of sophistication of your unknot, then all the time you will figure out that at least at one of the crossings, you're experiencing something strange like one or two colors, and you cannot color with the third one. Okay? And what does it mean? It means that, well, if the colorability property, three colorability of a knot, survives the Reidemeister moves, it means that basically, well, we said that two knots are equivalent if one can be turned into another with a series of Reidemeister moves, if Reidemeister moves, well, if they preserve the property of colorability, this means these are two absolutely different knots. Yeah? And that's an interesting story. So this is one of the invariants. Another one, that's to impress you. So basically, a lot of mathematicians were also doing, please raise a hand who knows what is determinant of a matrix. Okay. Actually, majority. And I'm happy with this. So then I will introduce this. So this is one of the polynomials that is introduced for the in the knot theory, and this is probably the most used polynomial called Alexander polynomial. It's not mine. This is the last name of the guy who proved it. So basically, what you can do, you can. So this is a diagram. What you can do, you can point a finger on the strain and then just follow this strain, and that's why I put here some errors. So you just follow the strain, and then, well, at some point you get to the initial point, right? And well, there are only two possible directions. You can do this way, but you can also do the opposite way, right? And that's why I'm just introducing here. So this is one way of the orientation, and there is just an opposite way of orientation. At every crossing, there are only two possibilities. So imagine that just symmetry breaking. So basically, if the left down to upper right gets kind of up, but you can, of course, rotate. So then there are only two options. So the other string that is getting through this crossing, it's either from the right bottom corner to the left up, or other way around. So there are only two possibilities for the crossing. So it's kind of one here, one there, or one here, another one there, right? If you put just any signs, any variables there, t, x, whatever, y, so you can create a matrix where you are just trying to say, at crossing A, at this crossing, you observe, so the labels are t1 minus t minus 1, so you introduce, so three edges, e1, e2, and e3, which are coming together at that point, and then you are identifying, actually at the crossing A, you have three different edges with three different labels. Labels are coming from the upper figure. You are making this matrix, you are computing determinant of this matrix, and the mathematician called Alexander have proven that actually, if two knots are equivalent, then the determinants of these matrices will be invariant, or they will be identical up to a certain factor which is quite distinguishable. So there is a multiplicator, you get rid of the multiplicator, it doesn't matter, but what remains as the polynomial, so this is the polynomial, quadratic, cubic, whatever, you have it identical for all equivalent to that very knot. Okay? That's the second. And you see there are a lot of other really interesting and very sophisticated invariants. Some people are saying that one invariant is good. Some people are saying another invariant is good. None of the invariants is so distinguishable that you can really play around and say, this is, so just compute something, this is a number or a polynomial or a color, whatever. This is really kind of a key invariant that distinguishes a certain series of knots, which is equivalent to one known one. There is no such, unfortunately. Oh, fortunately, because then mathematicians are creating even more invariants. Good. But fortunately, the life of node creators is quite easy. They are lazy persons, so actually, if you see nodes drawn on the table like this, or like trefoil, etc., they're quite simple, and the number of crossings is not that high. Then we should be able, so for some simple structures, for some simple diagrams, we should be able to find some kind of property or an algorithm that distinguishes, okay, well, we can unknot. And in fact, in 2020, together with a really nice group of people working in computer science, geometry, we were trying to actually establish such an algorithm that turns some complex knot or unknot of the simple diagram into much easier creature like unknot or like a known but simpler version of a knot. And we were actually succeeding with this. So I'm not diving deep into really details and mathematical definitions. For you to know what was the distinguishable feature of it, it's as follows. So imagine that you have two strains. You do only possibly two operations. So you twist it many times. It's the first picture here. Or you are poking many times or unpoking many times. So this one, it's just you have two strains, you poke and unpoke quite some times. So basically this one is twisting many times, this is poking many times. And then you take actually the spaceship and you fly really, really far away in the space, and you're observing these kind of simple strains. And you observe actually that the diagram, so then it becomes indistinguishable, these two strains. So it's just one, if you are far away in the space, it will be just one thicker line, right? And if you see that your resulting diagram is simple enough, following some mathematical properties, then you can easily distinguish, okay, this is kind of unknot, this is link, simple link, this is a simple trefoil, and so on and so on. So for this type of things, when, first of all, there are simple operations with the strains, and then from the space you see super simple diagram, then we know what to do. We know the algorithm that can unknot or that can turn the complex thing to the simpler ones. Okay. And we have still 5 minutes, and I have only 2 slides left. So basically, I promised you also to show the case when before you unknot, you have to sophisticate your existing knot. And this is a good example of it. So it's called yet another famous, it's culprit knot. How to unknot it? So if you don't look further than the second piece, then you, well, try first. So what do you think? So please don't look at the development further. Look at the first one and tell me what to do. It's quite sophisticated. How to unknot it? And actually, you don't see.
I see. First, you need to put strip from the back.
So the most back one, so it's this one, yeah?
And put it over the
Very
number.
good, very good. So you pull it, for instance, up, and then everything falls apart. So basically, if you scrape these four and you look at this one is exactly the result of what you are saying. So you're just pulling this one just up. So this part becomes actually this outer strain. Yeah? And then everything falls apart. Why? Because then you actually poke this part inside, it will become this. Then you unpoke this, and then there will be one twist, and you are done. Yeah, absolutely correct. Absolutely correct. Very good eyes. So, but there is one thing here. When you are pulling this back one outside, and that was the most clever move, what you do, you increase, so you have to pull it through the very sophisticated part of the map, part of the diagram, where there are a lot of crossings already. And you, by doing this, when you are pulling it, you are enlarging the number of crossings, not making it less, but you are making it more. And that's why, actually, you remember this really high polynomial. So before you do something simple, you should do something very hard. And that's why the number of Reidemeister moves before you really unfold or unknot something might first increase drastically. And then it will be getting to some, and maybe it's really iterative procedure. So maybe you start first increasing, then decreasing, then increasing, then decreasing. And this explains actually the size of the solution that you have to do when you are actually unknotting something unknotable. Okay? For you to know, there is a really nice bunch of knots which are not unknotable. So these are sophisticated. So the first one is unknot. But the other one, so there is really a classification and nice ways of creating something which is really different from the unknot. So for instance, this one, trefoil, that was overhand on the first slides. And for instance, this number 8, if you remember the surgical knots, there was number 8 there. So this is one of the surgical knots. And there are really a lot of other ones, and these are somehow become the seeds, the simplest unknotable things which are listed by mathematicians. And the question is, of course, so how to create this nice list, and how actually these knots which are present, for instance, in the in surgeries, on the ships, how did they evolve one from another? What was this kind of sophistication that brings us, for instance, from unknot from trefoil to 7-7? Was there any kind of historic reason for that, of usage of, for instance, this number 8? Or was it something special need from applications that brought us there? So these are really nice and interesting questions, and that's why, this is the last slide, that's why a couple of years ago, together with a colleague from Quantitative Economics, Andre Berger, and together with a colleague from FASOS, Anna Harris, we were trying to set up a project about evolutionary network, or how actually these nodes were evolved over time from historical perspective, from the crafting perspective. Anna Harris she is doing research on the crafting machinery, so it's a history of crafting, sewing and whatsoever. And well, unfortunately, this project didn't fly. Well, just we didn't have enough time, or we didn't put much effort in it. But nevertheless, I'm still fascinated with the stuff. So really, historic perspective, medical perspective, crafting perspective. So children are playing with these toys, with these ropes all the time, and it's interesting how these knots are evolving. And basically, maybe, and that was our hope and our kind of selling point for the project, that maybe it's interesting from the medical perspective, for those robots I was mentioning in the very beginning. So one-handed, 2 fingers, etc., etc. So, and if we create with somewhat a little bit sophisticated mathematical machinery a new knot, which is somehow applicable in the surgeries for a certain type of robots or for a certain type of surgeons, that would be something really cool. And with this, I probably have to stop, and I'm already over time. This is my Christmas tree for you, and this is also a Celtic knot tree, which is one of the first drawings of the knots in the history. Thank you very much. And I didn't use this machinery, not at all.